when the atom, the electronic cloud, or the orbits are spherically, symmetrically surrounding the nucleus positive charges. It is difficult to polarize that atom. When the cloud, the electronic cloud or the orbits are not spherically symmetric, they appear as polarized. Electropositive, electronegative, partially positive, partially negative. These are various terminologies where the atom is polarized in one way or the other way. The atom is relatively more positive on one side and less positive in the other side. So less positive is also negative in comparison to the more positive, right? So keep these in mind. A scientist mind must be very quick and sharp to pick things because you are playing with the lives of the people. If you design a material, design a component which is not performing very well and it is used in the aircraft, so you kill people. You are using it in a operation theater. You killed people by just ignoring a minor issue in the material, but the consequences are very, very huge for the community. Now, the simplest words I was talking to you about is that when the center of mass and the center of charge are coinciding, the atom is uniform. It is neutral. It is not polarized. And when the center of mass and the center of charge don't coincide, the atom is polarized. And when I was telling you, it has become a bit difficult now to see, but I had started with these two peaks, and I'm talking about this peak for the last half an hour, right? Now, if you want exactly this phase, then you will have to heat treat the material at the peak temperature for a longer time so that every particle of the material is crystallized into that phase. You need large crystals, and to crystallize in shorter time, heat treat the material at the peak temperature. You want small crystals, then start from here, heat treat here. So when you heat treat the material here and you have octahedra or ions or atoms, when you heat treat it here, you give kinetic freedom for this DAO unit to reach here, TiO2 here, and it forms PaPiO3. But if you heat treat the material here, then you give a little bit freedom, kinetic freedom, to this unit to combine with this. So if this phase is Ba2, Ti say 4 or something, then this phase will preferentially form. And this phase BaPiO3 will form when this unit find the kinetic freedom to reach this point. So the potential is there. You have enough ions of titanium, barium, oxygen in the material, but the kinetic freedom is not there. Then this will form a second phase within the material. So when you say that the optimum crystallization temperature for the formation of this phase is this means it is the most suitable temperature for the crystallization of that material. This never means that the material will not crystallize at other temperatures. The material will crystallize at all the temperatures within this peak, but the ideal temperature will be that one, and you give it the name optimum crystallization temperature. Secondly, this here, it will give local freedom to the ions, and the local freedom to the ions will form the very small crystals. Just local recombination will occur, and small crystal will form at many points. Small crystals will form at many points in the material. So if you need a large number of small crystal, then the ideal way is to heat the material here. If you need quicker crystallization of the whole volume, then the ideal way is this. So this peak tells you a lot about the material. But how can I confirm that this heat treatment at this temperature either form the phase or not? For that I go to XRD, X-ray diffraction. When you put the material, heat treated here, heat treated here, heat treated here in the X-ray diffraction machine, in the diffractometer, it tells me about that which phase has formed within the material. Number one. Number two, it tells me how much volume percent of the material has been crystallized. How much volume percent of the material has been crystallized. With the scientist's eye, you can easily know that if you crystallize the material and it gives you X-ray diffraction pattern like this, this means this portion is the crystalline phase and this whole area is the amorphous phase. So measure the area under the hump and measure the area under the peak, and it will give you the ratio of the crystallized portion of the material and the amorphous portion of the material. I did it and I found this, that 5% or 10% of the material is crystallized and 90% is amorphous. If I want the same crystal size, not exactly the same, but say small crystal size, and more crystallinity inside the material, then I will have to heat treat the material at this temperature for very long time. Small crystals, more volume fraction crystallized. Lower temperature, for a very long time. So it will give me small crystals more in number in the material. If I need short time and large crystal, then if I am heating this material for 500 hours, let's say 455 degrees Celsius, the same volume percent will be achieved. For example, this is 600 degrees Celsius and 2 hours. So much variation can occur inside the material. I can arrest phases. I can freeze the material in a specific state. What is freezing of material? What is freezing of the phase? I needed a phase which forms, let's say, 1000 degrees C, but below 1000, for example, at 900 degrees, and other phases forming. So what I need to do, I abruptly cool the material from 1000 so that it doesn't find time to reorient, to transfer mass within the material to form the undesired phase. So what I do, I suppress the crystallization of one phase and I enhance the crystallization of the other. So this is also in your control. how quick you are to make a specific phase, because it is just like you are running from here to the chemistry center and it is heavily raining and you don't want to get wet. So it depends upon your speed, that how quick you can run to minimize the chances of getting wet and reach there. The same thing is here. The rain is raining here. The phase is forming here. I need this state of material to come to room temperature. And once you have crossed this 900, for example, when you have crossed that 900, then you have, don't worry, it will not form that undesired phase, because you restricted the kinetic freedom of the material. The material potential want to go there and form that phase, but you kinetically restricted that. So how useful is the differential thermal analysis? Secondly, the material forms say this it is indicative of glass transition. It crystallizes, it transforms into glass. It is called TG. Remember the terminologies. A scientist who doesn't know the terminology correctly is not considered a scientist, and it is difficult for him as well as for others, right? So remember, hydration, dehydration, hydroxylation, dehydroxylation, glass transition, calcination, crystallization, crystal nucleation, melting. This is the whole story of the material, right? So glass transition means that it is a temperature. Glass transition is a temperature where a material remains as a glass, as an amorphous phase. Now, this is 1200 degrees centigrade, for example, right? I completely melted the material at this temperature, completely melted the material at this temperature, complete melting and homogenization. This part is for Muhammad Ali. Complete melting and homogenization are two different things. You may melt something completely, but what happens? This is the pot, the crucible, in which you put the glassy material. This glassy material contains iron oxide. This glassy material contains potassium oxide. It contains calcium. It contains magnesium. It contains silicon. Different sorts of material will be there. Some will be heavier atoms. Some will be lighter atoms. The heavier will go down. The lighter will come up. The more lighter will be volatile. So you will keep the temperature in such a way that all the existing bonds present within the material are broken, so that every ion becomes free to move, right? When they all becomes free to move, the heavier will go to the bottom and the lighter will come to the top, and the more lighter, the lightest one will be volatile. So you will be making sodium disilicate glass, but it will be not sodium disilicate, because you would have lost the sodium because of volatilization. So what people do in that case? In that case, people cover the crucible with something so that the ions cannot exit it. Secondly, they make a matrix within the furnace of the powder of the same material which is volatile, so that the environment of the furnace is populated with that type of ions, so that the volatile material ions which are running away are stopped from the outside. Thirdly, don't heat the material at such a temperature where volatilization occurs. So this is the job of the scientist, to make a compromise between the quality and the energy, right? Once the heavier are going down, the lighter are coming up. The only way is to put a stirrer here and a motor here, so that it stirs the glass while melting. So when it stirs the glass mechanically, you increase the chances of homogenization, and you will get a homogeneous melt from the material. When you got the homogeneous melt from the material, what happens? When you cool it down, and remember your path, your route is this, you are coming here. When you are coming from melting temperature towards the room temperature, when you reach here, there is heavy rain here, and you will have to pass this temperature so quickly that the ions never get a chance to form that particular phase. Then you have here, it is snowing here, and you want the material to pass the snow with no drop of snow upon it, no flicker of snow upon it. So you quickly cool it. But when you reach here, you have no worries, because you have frozen the amorphous disordered state of the material up to the glass transition temperature. Glass transition temperature has a specific quality. It allows slight reorientation to relieve stresses inside the material, but it doesn't give enough freedom to the material to crystallize. Enough freedom, local freedom, to release the stresses. These are two atomic planes. And this ion is missing here. So this will develop a loop type thing here. And you don't want this loop, it should be here. So only local reorientation is possible. And local orientation never result in bringing long range order in the material. When long range order in the material is not there, you are suppressing crystallization, you are avoiding crystallization, and you are keeping the material amorphous, right? Then when you reach here to the TG, what next? If you abruptly cool the material, what will happen? When you abruptly cool the material, abruptly cooling means this ion in the pen was here, and it was trying to pull apart, but you have frozen it here, right? So here is an effort to expand. In another place, there is another ion which tries to come to this way. So it leading to compression. One point in the same material is trying to compress, the other is trying to relax. And when you cool it down, it becomes brittle. It becomes solid. When it is solid and the compression want to press it, the expansion want to relax it, they both fight together and the material shatters into pieces. And that is what happening in the glasses. When you quickly cool the glass, leave it at room temperature, and it will split into pieces. It will be broken into pieces, right? So for that purpose, to avoid that, what people do, people heat the material. If this was, for example, the glass transition temperature, people select this place, not this place, but this place. For example, if this was 450, this will be about 400. And people keep a furnace at 400 from the night they started melting their glass. And when they take out the material from here, they quickly transfer it to the material furnace at 400 degrees centigrade. And that temperature is called the annealing temperature. And annealing temperature is basically for stress relief. It is neither forming a phase nor crystallizing a phase, but it just relieves the material of the stresses, right? Now, I did it. I combined different sorts of materials, and it was a glass former, and it formed a glass. But how do I know it is a glass? XRD. Take it to XRD. If it gives you an amorphous hump, this is glass, right? Now visualize it. Why are we getting amorphous hump? Why not peaks? And what is glass? Let me take you here. There is very little difference between these two. But this is amorphous and this is crystalline. What's the difference? There is translational symmetry here. There is no translational symmetry here. Otherwise, I am not making your board dirty, but this is silicon, oxygen, and like this. And every place you look, you are seeing things like that. But when it is like this, it is giving us sharp peaks. And when it is like this, it gives us the amorphous hump. Think about it, visualize it. The same things. Here is a point, for example, this is the unit cell. And X-ray beam is coming and hitting this place. Now, if this plane is fixed, what will happen? All the monochromatic beams of X-ray will hit this place and you will get a diffracted spot here. Similarly, all the X-ray beams hitting this wall of the unit cell, which is the atomic plane, will hit this place and will give you a spot here. But if everywhere this is plane, this means there is no long range order, although short range order is there. But the short range order, all are giving you a diffraction like this, and you get a heap of stone, a Poisson type distribution at one place. And that one place is associated with these SiO4 tetrahedra. So this short range order is giving you a Poisson type distribution of the diffracted beam. It diffracts the beam, but it cannot distinguish between different areas because there is no translational symmetry. Everything is giving you the same diffracted beam, and the same diffracted beam comes here. This classroom is like a unit cell. Somebody is throwing stones from outside. So you have 3 windows. And when in the evening you check this room, every window will put the stone at a particular place. And you will have 3 heaps, 3D of stones at different places. But if there is no window and the whole wall is a window, then you will have a big heap because there will be no difference between the two. So there is no specific order in the diffraction. So visualize things with your mind and understand it according to your frame of reference, according to your frame of wisdom, that how you visualize things. Then discuss it with other people that I am thinking like that. Am I right? Because I tell you again and again that the mankind for thousands of years didn't understand and didn't believe that the earth is moving. And those were not ordinary human beings. These were Plato, Aristotle, and such people who never believed that the earth is moving. And for thousands of years, so never 100% believe on your perception. Discuss it with other people. Consult the books, consult the research papers, and then say something, because you are mastering and you are doctoring the subject of physics. And if a statement comes from you which is not reliable, then what will be the outcome of the science? Right? So, I am talking about the same small peak of the differential equation like that. So, this small area or this small plot of the differential thermal analysis in which you put 5 to 10 milligrams of the reference material and 5 to 10 milligrams of the material under test, and you heated it from room temperature to say 1200 degrees centigrade, and you can write a book upon it. There is so much information in this small plot. But as a scientist, I told you that the whole world of science is moving around the transformation of phases, the reaction of materials with other materials, and when you come to the electrical properties, the electronic properties, you are playing with the small atom with the nucleus in the center and the electronic cloud in the case of metals and the electronic orbits in the case of non-metals. And that behavior of the electron is governing the whole principles and the whole ways of technology in the modern world. Now, as a beginner in the research, the first thing you do, I told you, take the raw materials as a material scientist, heat them up, preheating, which I told you, oxides at 800, carbonates at 180. Exactly measure the weights, the stoichiometric weights you need for the final phase. When you guard those stoichiometric composition, that is called batch composition, BATCH, batch composition. When you physically mix the initial ingredients, physically mix the initial ingredients is called the batch composition. When you got the batch composition, then if you are careful, do the DTA of the mixture. Do the DTA of the mixture, it will give you the overall picture. When I was, particularly I had a background in physics and I started engineering material, then I was not convinced on many things. So, for example, if I was making a porcelain material and the porcelain material needed clay, feldspar and quartz, then I tried to individually heat treat them. That what happens if I heat treat the quartz, when I heat treat the feldspar, when I heat treat the clay. They told me the changes in the materials with temperature. Now, for example, I heat treated the material at 454 for 90 hours. Because I am checking, as a scientist, people say the material will transform to a glassy phase at 454. But did I do it? If no, then you are not confident of what you are saying. So I did it. Right? I did it for 90 hours and I did very slow XRD. Remember, I told you that XRD can be in many ways. You can put a solid sample in the XRD. Right? You can make fine powder and put it in the sample holder of the XRD. You can make a fine slurry of the powder in acetone or something and put it on a thin film and do XRD of that. There are different ways of doing XRD. You can make thin strips of a metallic material and fix it on a glass slide and you can take into XRD. But when you take such material to XRD, what happens inside? I put this solid piece in the XRD and the material crystals are preferentially oriented. Preferentially oriented is that, for example, the C direction of all unit cell is like this. And when the XRD hits it the CX is more than the A and B axis. This is just like all of you are sitting in this room and suddenly go here to the windows and just put your head like this. So from the outside person will see only heads. They will not see the bodies. So the crystals had A and B axes, but the preferential orientation just showed the C face to the X-ray. So X-ray is not blind like us. It can see things. But the frequency of diffraction, the intensity of the diffracted rays from the C-axis will be more in comparison to A and B. So what will it give you? It will give you a diffraction pattern like this. C001. This is, for example, 101, this is 201, this is 102 or 202, something. These are the scale indices. It gives you maximum intensity for this. This is wrong. This is wrong. Because when you compare the data with the theory, then the theory gives you, for example, not the 001 as the maximum intensity peak, but it gives you, for example, someone here, 111 is the maximum intensity peak. So if your results are not consistent with the literature, this means there is something changed either in your experiment or in the experiment of that person, right? So I avoid putting solid sample into the material, into the X-ray diffractometer. I prefer to finely grind, to make it fine powder and put it in the XRD. How XRD looks like. This is a dip in the sample holder. This part goes into the grip of the sample holder where you put the machine. The X-ray radiations are coming here and they are diffracted in different directions. So if I fill this place with powder and finely smoothen the surface, I am giving every plane of the crystal equal opportunity to be scanned by the X-ray beam. When a large number of particles are there, it will give a statistical distribution of the crystals facing the X-ray beam, and it will give me a more reliable information, and then I should expect that my X-ray diffraction pattern will be reliable and it will be consistent. The 111 will become here as per theory, and the 001 may have here, because you are measuring the intensity of the diffracted peaks. If the diffracted peaks are coming at specific angles, they are qualifying the n lambda is equal to 2d sine theta, the Bragg's diffraction equation, the condition, then they will give you specific peaks at specific points. If they are not meeting that, then it will not diffract. It will diffract, but the diffracted beams will destructively interfere and there will be no intensity, because common sense says that when X-ray is coming here, why don't we have peak here? Right? This is because at these angles, the Bragg's diffraction criterion is not met. Remember this, a scientist must have a solid answer. If I confuse you, this means I am not understanding it. So never keep yourself confused. In science, you have answers to many things. Yes, we cannot make a flying man. We cannot do many things, but never think that everything is blind. There are answers for many things. And if there is no answer, then you are a fortunate person to look at answer for that, and you are the main scientist of the society when you discover things. But if you don't bother to reach the truth, the reality, the logical answer, then you are not a scientist. So struggle to find the real answer. So powder is the best way for phase analysis, for crystal structure analysis. Now, I was telling you that I heated it for 90 hours, not for 1 hour, 2 hours, 3 hours, 4 hours, 90 hours, to make sure that there is not enough kinetic freedom inside the material to crystallize. I melted the material, cleaned it, grind it, so that both the surfaces were shiny. Then I heated it for this long time. I looked into the sample in the microscope. I looked into the sample in the XRD, and there was no variation there. There was no systematic features there. If I don't see any systematic features in the sample, this means there is no long range order inside the material, and the material is amorphous.